Let's start today by looking at number 6 from section 2.4. It's another verbal description problem where you have to understand how to interpret the derivative in this context. Number 6 says high-speed internet download speeds generally cost more. C equals f of s is some function that gives you the monthly cost in dollars for speed s in megabytes per second. It's good, I think, right away when you write down this kind of equation, C equals f of s, to go ahead and write an arrow like I'm doing and mark what the units are. C is a cost in, or monthly cost, I should emphasize even, monthly cost in dollars. S is your internet speed. Probably, okay, it does say it's a download speed. It's a download speed for your internet in Mbps. That would be megabytes per second. You could also write that as MB/S for megabytes per second. That already is a rate of change. How fast are you downloading the file? How many megabytes every second on average? That's already a rate. It's not, in a sense, it is a derivative already, but we are going to be interpreting the derivative of this function. So it's almost like we're interpreting the derivative of a derivative, like an acceleration kind of, in the end. Yes, part A says, in words with units, give interpretations of the fact that f of 10 is 40 and f prime of 10 is 2. Let's also draw a graph, even though it's not requested. Now, it's very possible that you could have an internet service whose cost as a function of download speed is a linear function. That's very possible. Straight line. Is that always what happens? I don't know. I haven't kept up enough with internet costs. Actually, they usually do packages, right? Where you get a certain fixed download speed and a certain fixed cost. And if you want the next download speed, that's one higher level, so to speak, you have to pay one other cost. So this is probably in reality more of a step function that has jump discontinuities. But for the sake of simplicity, assume it's not. Would it be concave up or concave down if it's not straight? That all depends on the internet service provider. What do they want to do? If I had to guess, I'd guess maybe concave up. Because once you get to high enough internet speeds, it's, maybe you might say that's really high technology and that's really costly. Now, that's just a wild guess on my part. You could also argue it's concave down because maybe it's getting more efficient cost-wise for even higher speeds. But that's my rough guess. It really doesn't matter much for the purposes of doing this problem. I'm just trying to use my imagination. And imagination is important in math, including calculus. You need to take these kinds of descriptions and translate them into pictures in your mind and think about possible graphs and what it would mean. F of 10 is 40. So when the download speed is 10 megabytes per second, the monthly cost would be $40. And that would be the answer for how to interpret f of 10 equaling 40. I just said it verbally. When the download speed is 10 megabytes per second, then the monthly cost is $40. You could write that down if you want. Okay, if I don't take the time to write that down, I will write down the interpretation of the derivative. What's the derivative fact here? The derivative fact is that f prime of 10 equals 2. Let's write that down. And let's do the same thing we did last time and also write this in Leibniz notation. The variables are C and S. C is the dependent variable, S is the independent variable. The cost depends on the speed. The derivative is the rate of change with respect to the dependent variable. the cost in this case, with respect to the independent variable. Where does this notation come from, by the way? It is related to delta notation, right? Delta is the Greek version of D. It is related to the fact that, technically speaking, the derivative here is the limit we've typically written as h goes to 0 of a difference quotient. But to be suggestive, well, I'm going to let h be delta s. Shouldn't have made my bar so big. Delta s is the same as h. Delta s, the change in the independent variable, is the same idea as h, letting the independent variable change a little bit. Before we wrote f of a plus h minus f of a all divided by h. In a shorthand form, that could be written as delta s over delta t. If I wrote this with function notation, it really does mean the same thing as this. Where I'm using a delta s. I meant, I got confused, sorry. I got confused by my variable names. This is a c and this is an s. For some reason, I went back to thinking about the application as being some function of time. Scratch that out. F of the independent variable is s, not t. S plus delta s minus f of s all divided by delta s. This is the same kind of limit we saw before, except we're using different notation. S is like x. Delta s is like h. This is like f of x plus h minus f of x all divided by h. But this expression in the numerator is a change in the function value. It's a change in the cost in this case. It's the same thing. And because delta is the Greek version of d, that's why we use the d's over here. Evidently, Leibniz was thinking about that when he first came up with this notation. Anyway, that's a side note. As far as doing the problem goes, we're given that the derivative evaluated at, when the input s is 10, evaluated at s equals 10, f prime of 10, we're given that that's 2. The input, 10, is still a value of s. It's still a download speed. The value of this function, the value of this derivative is, well, it's units of the derivative itself, which, since I'm using Leibniz notation over here, I'm trying to remind you that the units are units of s per unit. Why did I do the exact same thing? I didn't have my coffee this morning. I'm sorry that this is on the video, and now I need to just. I'm so used to thinking of physics applications where s is position, actually, not speed, and t is time, but that's not the application here. Units of c per unit of s. Dollars per megabyte per second. And that's the units of the number. This is in dollars per megabyte per second. Abbreviated MBPS. I also could write this as dollars per, and maybe use parentheses, megabyte per second. And you might think, could I simplify those units to like seconds times dollars over megabytes? Well, you could, but that's not very pleasant. Not very intuitive. So it's better to leave it like this. That helps you interpret it. Graphically, it represents the slope. The slope of the tangent there, f prime of 10 is 2. Now, I've drawn it to look like it's more than 2. Looks, well, at least on the scale, it looks like it's more than 2. Don't let the drawing fool you if the drawing does fool you. What does this mean? This means when the download speed is 10 megabytes per second, all right, that is Mbps, the rate of change, the derivative is the rate of change of the monthly cost C with respect to the download speed S is exactly what I say up here, $2 per megabyte per second. But don't stop there. Say something like this. So if the speed, download speed increases to 11 megabytes per second, you get a slightly better service by paying a little bit more. The cost should go up by $2 per megabyte per second times 11 or times 1? Times 1, not 11. 11 is the actual speed. But the change in the speed, delta S, is 11 minus 10 is 1 megabyte per second. And that's what goes right there. You always multiply the rate of change, the derivative, by the amount of change, not the actual internet speed of 11 in this case. It's the fact that it increased from 10 to 11. It increased by 1 megabyte per second is the reason you multiply by 1 megabyte per second. Don't multiply by 11. This simplifies to $2. The megabyte per seconds cancel. That's why it's important to think carefully about your units. And then we could add what it goes to. What will the new cost be? The old cost when it was 10 megabytes per second was $40. So it's going to go up by 2 to 40 plus 2, $42. What I'm using right here is what's called a linear approximation. I used it in this case with delta S, the change in the speed, equal to 1 megabyte per second. But I don't have to use it just for a 1 megabyte per second change. I could use it for a 0.1 per megabyte per second change, or a 1.7 megabyte per second change. Delta S can really be anything, though the approximation is going to be better the smaller delta S is. In general, the change in the cost, written as a delta S, not a ds, is the derivative, the rate of change, times the change in the independent variable. This is an approximate equation. The approximation gets better and better for most applications, the smaller delta S is. But I could use it for other delta S's as well, like 1.7. If delta S is 1.7 megabytes per second, So you've gone from 10 megabytes per second to 11.7 megabytes per second. That means the change in the cost is approximately $2 per megabyte per second times 1.7 megabytes per second. Cancel the megabytes per second. You would approximate it to be $3.4 to be the change in the cost. So if the old cost was $40, you would expect the new cost to be $43.40. If the graph truly is concave up, like I was pretending here, the linear approximation is going to be too small, because the linear approximation really is using the tangent line to approximate the curve. If the curve is concave up, the tangent line will be below it. And the approximations you get from that tangent line will be too small because it's below the curve. When a curve is concave down, then the tangent line is above the curve and the approximations are too big. So if our curve's concave up, this approximation here is probably a bit too small. The real cost is more like $42.10 or something. We're using the fact that this curve is smooth. That word smooth is actually very important in math. It doesn't have any corners in it. It doesn't have any jump discontinuities. It's a nice smooth curve, and so the tangent line approximation is a good approximation to the curve when you are close to the given point. That's linear approximation. We're using the fact that the smooth curve is locally linear. If you zoom in near any point, it looks more and more like a straight line. Let's do another example, and hopefully I won't get messed up. Number 8 is an economics problem. An economist is interested in how the price of a certain item affects its sales. That's like supply and demand. At a price of P dollars, a quantity Q of the item is sold. Now, there's some stuff they're not telling you here, like how long is the sale going for? A day, a week, a month. They're not telling you that. If Q equals F of P, explain the meaning of these statements. F of 150 equals 2,000. F prime of 150 equals negative 25. So Q, the quantity sold, is a function of the price. It should make good intuitive economic sense that as the price goes up, the quantity sold should go down, right? You're going to buy a bike, and these bikes are selling for $1 million, you're not going to buy a bike. If it's selling for $1, you're going to buy it. Lots of people will buy it. As the price goes up, the quantity sold should go down. The quantity sold should be a decreasing function of price. And yeah, as the price goes to infinity, the quantity sold should go to 0. So probably it's concave up like this, with the p-axis as a horizontal asymptote. Would the q-axis be a vertical asymptote? Well, in reality, no, because you're not going to make an infinite number of whatever you're selling. But for the purposes of economic theory, you kind of pretend you can make an arbitrarily high number of bikes, for example. So it often doesn't hurt to pretend you got a vertical asymptote there. But Q is a function of P. F of 150 equals 2,000. When the price is 150, the quantity sold is 2,000. The scales on these axes are not the same. This 150 is in dollars. That certainly is a typical unit used for price. It might not be a bad idea to think of the units slightly differently as dollars per item, dollars per bike. Let's leave it at dollars at the moment. The quantity sold is the number of items, the number of bikes. Items sold. F of 150 equaling 2,000, I'll just say it, means that when your price is $150, you're going to sell 2,000 items. Again, during some period of time. That's not specified. What is F prime? F prime is negative 25. Yes, geometrically, that means the slope of the tangent line to the curve at that point. The slope there is F prime of 150. It's negative 25. What are its units and what is its meaning? In Leibniz notation, I won't make a mistake this time, it's dq dp, the rate of change of quantity sold with respect to price, evaluated at p equals 150. When the price is $150, the rate of change of quantity sold Q with respect to price is negative 25 items sold per dollar. Units of Q per unit of P. So if the price increases by, say, $1, I'll go ahead and use delta notation. If delta P is $1, the price goes from $150 to $151. Then the quantity sold will change by delta Q is approximately negative 25 items per dollar times $1. The dollars cancel. This becomes negative 25 items. Bikes, if the items are bikes. Another way to phrase that is to say you would expect the quantity sold to go down by 25 items. You could phrase it that way too. The change in the quantity sold is negative 25 items. That's the same thing as saying the number sold goes down by 25 items. You technically can phrase it either way. I'm fine with either way. Maybe for the grader's sake, phrase it this way with a negative sign and emphasize it's the change in the number of items sold, instead of saying the number of items sold goes down by 25 units. It means the same thing. You can even say both just to reassure yourself about you understanding the meaning, and just in case you're worried the grader might think about it some other way. You could even say both. This graph is also concave up, so this tangent line approximation is too low. The true change in the quantity sold will actually be a little closer to zero, maybe negative 23 items instead of negative 25. You could say the new number of items sold is the old amount, 150, plus negative 25. We did an approximation symbol there because that's an approximation symbol there. Wait a minute, not 150, 2,000. There were 2,000 items sold when the price is 150. 2,000 plus negative 25, which is, yes, the same as 2,000 minus 25. 1,975 items would be your linear approximation to the number of items sold if you raise the price from $150 to $151. And yes, it's probably a bit too low. Probably it's going to be more like 1,980 items or something. What I'm using here is effectively the equation of a tangent line. Though it doesn't look like one, does it? If y is a function of x, I just wrote down in the previous example that delta y would be approximately f prime of x times delta x. That is the same approximate equation as this one. F of x plus delta x minus f of x is approximately f prime of x times delta x. And f prime of x times delta x can be thought of as f prime of x times a difference. X plus delta x minus x. Effectively, what we've got here in comparing this with this is like the point slope form of the equation of line, just with different notation. This is very much analogous to y minus y1 equals m times x minus x1, just with different notation. It's the same kind of idea. Y minus y1 is like a change in y values. It's a change in function values. M is a slope, just like the derivative is a slope. And this is a change in x, just like that's a change in x. Don't let the different notation bother you. Focus on the idea. This is the equation of a line exactly. That's an exact equation. This is an approximation here because I'm really using the tangent line to approximate the curve. F has a graph that's a curve in general, not a straight line. Sometimes the questions get weird, but we want to be able to handle it. Number 9 says the atmospheric pressure at a point h meters above the surface of the Earth is P equals F of H torr. To tell you the truth, I've never heard of the units of torr until I saw it in this book before. Right? Usually the units of pressure are like atmospheres or something, right? Millibars, things like that. I haven't heard of torr before. Give practical interpretations of these statements. F of 500 is 708, and F prime of 500 is negative 0.101. If you didn't know this already, you should know that the atmospheric pressure goes down as you go up. Pressure as a function of height is decreasing. You go to a top of a mountain, you know, the air is thinner. If you go to the top of Mount Everest, you can't survive for more than a couple hours without oxygen. You're in the death zone. Even if you're just sitting there, you won't survive. Even if you got tons of layers of clothes on with coats, so you're not cold, you won't survive without, there's just not enough oxygen up there because the air is too thin. The atmospheric pressure is too low. As the height above the surface of the Earth goes up, the pressure goes down. So this is going to be a decreasing function, probably concave up again. Probably not with a vertical asymptote here, because right when you're at a height of sea level, the pressure is not infinite. So this could be a graph of the pressure as a function of the height above sea level. Pressure being in torr. Never heard of that before reading it in the book. H being in meters above sea level. You might wonder what causes the pressure to go down as you go up. It's because there's less atmosphere above you. That's why. That's why the pressure goes down. F of 500 is 708. when the height is 500 meters above sea level, you know, of that somewhere between 1,500 and 2,000 feet. In Minnesota, we would call that a mountain. In Colorado, they'd call it a little hill. The pressure is 708 torr. I'm not going to write it down. That would mean what I just said. When you're 500 meters above sea level, the pressure would be 708 torr. Always? No, it would vary depending on where you are, depending on whether there's a high pressure system or a low pressure system in the atmosphere. This is probably an average. F prime of 500 equals a small negative number. dP dH evaluated at H equals 500. F prime of 500 equals negative 0.101. What are the units? They'd be units of P per unit of H. Torr per meter. So say you're at 500 meters. You decide you want to go up another 100 meters. Not just 1 meter, 100 meters. What would the new atmospheric pressure be approximately, according to this? Delta P is going to be approximately dP dH times delta H. I'm not bothering to put the evaluate line there. Don't let that bother you. It's understood we're dealing with the given situation. This is going to be negative 0.101. And if I go up by 100 meters, I do multiply by 100. Not a very small number. Though it's possible this still could be an accurate approximation, even though delta H is fairly large. It depends on how straight the graph is on the given scale. That affects how good the linear approximation is. Do this multiplication, you'll get negative 10.1. Units would be torr. That would be the approximate change in the pressure. So the new pressure would be approximately the old pressure, 708, plus negative 10.1. Yes, that is the same as 708 minus 10.1. That would be 697.9 torr. And to tell you the truth, because it's a linear approximation, that's probably too many significant digits. You'd probably want around to 698, maybe even 700. Is it too big or too small? Because the graph's concave up, the line is underneath, so it's probably too small. The true answer is probably closer to 700. But we don't really worry too much about significant digits in this class. This would be fine to do. In science classes, you do need to worry about significant digits, okay? They want you to do that. I don't make a real big deal of it, because we're focused on a different subject. We're focused on understanding the math. So that's a pretty good mix of some problems from section 2.4. None of these problems say to make graphs. I just like making graphs to help me understand it. There could be some graphical problems later on, I suppose, but I'm not seeing any offhand. Some of the problems are tricky. Maybe we should do one more tricky one here. Oh, this is another one about altitude and pressure. Now in kilopascals instead of torr. I should have probably just done this one from the start. I don't want to do 38 completely, but let's see if we can make sense of the last two parts of it, parts C and D, because they're a little different. Notice they involve the inverse function. So it's a very similar situation in 38 here is the problem we were just talking about. We're still talking about pressure as a function of height. Units of pressure are now kilopascals instead of torr. H is in, another thing to be careful of. H is not in meters, it's in 1,000 meters. That matters. So it's still a similar graph, same letters, P and H. P is a function of H, but now P is in kilopascals. H is in 1,000 meters. Doing parts A and B would be very similar to what we just did in the previous problem. But what about parts C and D involving an inverse function? And does this function even have an inverse? Well, yeah, it's 1-to-1. It passes the horizontal line test. No horizontal line goes through it more than once. What would the graph of the inverse function look like? Should I draw y equals x here and reflect it? No, you should not. Because the variables mean something. And if you draw it in the same picture with the same labeling for the axes, that's wrong. You really need a completely new graph with different labeling for the axes, P horizontal and H vertical. Will the graph look like some sort of reflection? Well, kind of, but because the scales on the axes are going to be different in general, it's really mostly the shape of the reflection we're after, and the shape would look something like this. That'd be the shape of an approximate reflection across this, but I did change the labeling of the axes. H is F inverse of P. We don't know the formula. That's okay. We don't know the formula for F either. F inverse of 10 equals 17.6. When the pressure is 10 kilopascals, that's a P value now, not an H value. The height is 17.6 thousand meters. By the way, that's high. That's really high. That's higher than Mount Everest, right? Mount Everest is close to 29,000 feet. In meters, that's the ballpark of 10,000 meters. 17.6 thousand meters is way above that. Like, it's like 50,000 feet high. Way above where airplanes go. I was on an airplane coming back from Hawaii this summer, and we were actually at 40,000 feet, which I thought airplanes usually cruised at 30,000 feet, but we were actually at 40,000 feet. They showed the temperature outside. The temperature goes down as you go up. It said negative 85 degrees was the outside temperature when we were up at 40,000 feet. Not only does pressure go down, but the temperature goes way down as you go up too. That's why there's snow at the peaks of mountains, even when it's warm down below. What about the derivative? F inverse prime of 10 equals negative 0.76. Because it's the inverse function, it's this one, not this one. That derivative fact is a rate of change of H with respect to P. Another thing confusing here is it makes more sense to think of pressure as depending on height than height depending on pressure. Right? Doesn't this one make more sense? As you go higher, the pressure goes down. It doesn't make much sense to say, as the pressure goes up, the height goes down, though it's still true on average. Mathematically speaking, even though that doesn't make much physical sense to think about, mathematically speaking, we can still think about it. This graph is still the graph of a function because this one passed the horizontal line test, this one passed the vertical line test. So this is a rate of change of height with respect to pressure. When the pressure is 10 kilopascals, this rate of change is negative 0.76. That's F inverse prime of 10 in the book's notation What does it mean? What are its units? It would be units of H per unit of P. 1,000 meters per kilopascal. 1,000 meters per kilopascal. How would you interpret that? You could, for example, say if the pressure goes up by 1 kilopascal, the approximate height went down by 0.76 thousand meters, which would be 760 meters, which is pretty far. That's like 7.5 football fields long. Pressure goes up by 1 kilopascal because you were going downhill. This is approximating how far you went downhill. The change in your elevation was negative 0.76 thousand meters, 760 meters downward, if you didn't know you were going downhill already. Weird, but true. Okay, so you got to have some mental flexibility.